Okay, so now we're going to switch gears and talk about another completely different topic. So, to give us some context as to where we're at in general chemistry and where we're going to go, there's really, when we look at Gen Chem 1 and 2, there's really three major questions that we have to ask. So, Gen Chem 1 and 2 sets out three really key chemical questions that we're trying to figure out. So, one of the questions is we ask, what happens during a process? Okay, so in order to look at that, in order to answer those questions, that was the basis of everything that we talked about at the very beginning of general chemistry. So, that for us, that was chapters for interactive general chemistry, that was pretty much chapters 2, 3, 4, and 5, where we wanted to know how a chemical reaction works. We also talked about stoichiometry. So, the explanation to what happens, we studied chemical reactions, and then we also looked at stoichiometry. Okay. Now, the other thing that we want to take a look at, the next question is, to what extent does this process happen? So, to what extent does the process happen? Now, to answer this question, this is what we're going to be looking at in the next group of chapters. So, when we take a look at chapters 15, which is chemical equilibrium, and then 16 with acids and bases, 17, which is going to be getting into examples of acid-base equilibria, buffers, and then we're going to get into solution equilibrium. Okay, so to answer this question, we're going to be studying something called chemical equilibrium. And so that's the major part of the second unit of this course, answering that question, to what extent does this happen? How do we quantify that? The third question that we want to ask is, how fast does this process occur? So how fast does it happen? And to answer this, we're actually going to use this chapter. So in order to answer this, we're going to look at rates of reactions. And rates of reactions tend to be very highly variable. Okay, so how fast a reaction occurs is actually a pretty critical question, because the range is enormous. Because you can have reactions that occur in milliseconds or faster, and then you can look at chemistry, especially geological chemistry, which takes place over centuries and millennia. So the study of a rate of a reaction is actually called chemical kinetics, and so that's what we're studying in this chapter, chemical kinetics. This is concerned with the rate of a reaction and the sequence of steps by which a reaction occurs. Okay, so chemical kinetics is concerned with the rate of a reaction and then the sequence and steps in which a reaction occurs. So this chapter is actually divided into two segments. First, where we're looking at the rates of reactions and figuring out what we can ascertain from that information. And then the second part, the sequence of steps in a chemical reaction. Okay, and the sequence of steps, we actually give it a special name for this. This is called a mechanism. If you've ever heard people freak out in organic chemistry because of these reactions and these mechanisms, that's I'm going to introduce that here, but it's actually not as bad as you think. So yeah, don't worry. So some examples of processes for which chemical reactions are important include that in the body we use oxygen in respiration, in which must occur fast enough for us to live or even run. Okay, if we have a fire needs fuel, and it needs an oxygen source. to be added fast enough to sustain combustion like the space shuttle. Okay, pharmaceuticals must be produced at a rate sufficient to be cost effective and be used in the body at a rate sufficient to produce a desirable effect. Okay, now one of the keys of this semester is the mathematical description of chemical kinetics. Now, and so that's a big portion of what we're going to be looking at in this chapter, letting the mathematics tell the story. And so, in order to tell that story, we have to use calculus. Okay, now before you guys freak out on me, I'm gonna try to introduce as much of this as possible through algebra. So as long as you've had exposure to college algebra, pre-calculus, you'll be okay. So I'll try to explain the mathematics as we go. So don't worry if you're haven't had that yet. You'll be fine. All right. So in a general sense, what experimental parameters will affect the rate of the reaction? There's actually three things that will affect the rate of a reaction. First is concentration. Second, temperature. And those two we have a lot of control on. The third, molecular size. So that being said, let's define what rate really means. So when we're talking about reaction rates, we're talking about the change in concentration divided by the time change. Now, if I was going to write this as a fraction or in like a mathematical equation, to simplify the change, in math and algebra, we talk about change as a delta. So we represent it with a triangle to represent change. Okay. Now, to represent concentration, what we do is use a pair of brackets to indicate concentration. So, for instance, if we were talking about the concentration of a certain species, let's call that species A, I'd write a set of brackets, and then inside the set of brackets, I would put A. Okay? Now, to represent the time change, I'm going to use another delta symbol, but this time I'm going to use a lowercase t. And so this little expression, this is how we mathematically show the rate of a chemical reaction. It's going to be expressed as the change in the concentration divided by the change in time. And again, it's common to use brackets to talk about concentration. Okay. Now, one way to look at rates is to use a simple analogy. So let's say we were in a really, really large lecture hall, and that lecture hall had 200 students. Okay. Now, as students leave the room at the end of the class, we could actually define a rate of departure. And so we could define that rate as something like this. The rate would be equal to the change, and I'm going to use another set of brackets. And inside the set of brackets, I'm going to say the number of students, okay, divided by the change in time. And so that would be our rate. Now, if let's say we had 45 minutes, if we had 45 students that were leaving per minute, the rate would look something like this. We would say 45 students are leaving the room, okay, divided by 1 minute. Now, because the students are leaving, we define that since they're leaving us, that would be a negative. If they were coming into the room, we would say that that was a positive. Okay. Now, before we get into any further, let me ask a question here. Is this rate constant until the room empties, or would the rate change as the concentrations change? Okay. So as the concentration change, will the rate change or does the rate stay the same? So basically is, every minute are we still losing 45 students or does that rate actually change? And so the answer to the question, the rate's got to change. The rate must change. And think of it this way, after class, everyone's in a hurry to get out of the classroom as fast as possible. So you're going to have a larger departure rate. A lot of people leaving the room all at once. And then after 2 minutes, that rate's going to slow down. So the rate's got to change. Now, here's where it gets kind of interesting, though. If the rate changes, and we said it would it increase or would it decrease over time? And here's the question. Would it increase or would it decrease? Well, ideally, if all the students are leaving all at once, the rate would decrease. But if students stay behind, there could be a larger increase at some point. So to answer this question truthfully, the rate has to fluctuate. Okay, so if we were going to graph this, what would the graph look like? It would look something like this. If I drew, let's say I draw a simple graph on the y-axis, I'm going to put concentration, so I'm going to put a pair of brackets. The x-axis, we're going to have time. And so the way that this graph would look like, we would start at a point where we know we've got everybody in the room, and eventually, at some point, that curve is going to hit 0. Now, at some point on this curve, since this is not a straight line, what we could do is find this, pick a point on this curve. Let me use a different color for this. What we could actually do is find the slope of a line that's tangent to that point. So I picked a point on this curve and then drew a straight line that's tangent. Now, if I was able to find the slope of that line, okay, again, that's rise over run. Let me do that a little bit better. Okay, so if I was able to find the slope of that line, m, that slope would be negative change in concentration divided by the change in time. Okay, so that's what a graph would look like. All right, so that being said, now that we talked about, what a rate should look like, what the rate would kind of do, what a graph would look like, let's talk about this in terms of a chemical situation. Okay, so here is our chemical example. We've got 2 moles of N2O5, which is a gas, and that breaks down to form 4 moles of NO2 and 1 mole of O2. Okay, so again, left-hand side of the arrow, this is your reactant. Right-hand side, the NO2 and the O2, those are your products. Okay, so we can actually follow the progression of this reaction in 2 ways. One way, if you look at this, since you're going to have 5 moles, 4 moles of NO2 plus 1 mole of O2, since you're going to have 5 moles of a gas on the right-hand side, and you're only going to have 2 moles of a gas on the left-hand side, the pressure should be increasing because the number of moles is increasing. So one way that we can follow the progression of this reaction, the pressure should be going up. Okay, so that's one way. Now the other way, if you study this chemical equation a little bit more, NO2 actually gives off a pretty brown color, like brown like mud. Okay, so we can actually follow the progression of this reaction by looking at the color, because as more NO2 is being produced, we should see a definite brown color. Okay, now that being said, let's take a look at the results of this reaction. We're going to measure the concentration over time for N2O5, NO2, and O2. So there's two ways that we can show this data. One way is to show it graphically, and that's what we got here. So this particular table has the concentrations of N2O5, NO2, and O2 at certain points in time. All right, so that's one way to do it. Another way is that we can graph all of those data points and then put them on a curve, and that's what we got here. So we got a lot of information. So what we're going to have to do now is to sort through this information and try to see what we can ascertain from this. All right, so let's go back to this table. Let's take a look at what we got. So the first column is going to be our time. We're measuring that in seconds. Second column is going to be your concentration of N2O5. Okay, so here's your reactant. I'm going to label that as R. For the NO2, we know that's a product, and O2 is a product, so I'm going to label those as products. Okay. All right, so let's see if we can suss out any patterns from this. All right, so N2O5, the concentration of N2O5 at 0 was 0.02 molar. Okay, and at 100 seconds, the concentration went down to 0.0169 molar. At 200 seconds, the concentration went down at 0.0142. Concentration at 300 went to 0.0120. So is there a trend here? Yeah, we're seeing that as we go from 0 to 100, and 100 to 200, and 200 to 300, and so on, it seems like the number is decreasing. Okay, so I'm going to put a minus sign here just to show that the concentration is decreasing. It's going down. Now, what about NO2? Concentration of NO2 at time 0 is 0. Well, wait a minute. Does that make sense? Well, think of it this way. So at the beginning we're saying with this concentration being at 0, we're saying that the only entity that's present at the beginning of the reaction is N2O5. Okay? And eventually you start producing the NO2 and you start producing the O2. All right. So let's say, okay, so time 0, the concentration of NO2 was 0. At 100 seconds, the concentration is 0.0063. Concentration at 200 seconds, 0.0115. Concentration at 300 seconds, 0.0160. Concentration at 400 seconds, 0.0197. So we know that these numbers are increasing. And if we take a look at the numbers for O2, they too are also increasing. Okay, so we're cool on that. Now here's the other cool thing. If you take a look at our chemical reaction again, it's saying that you're going to form 4 moles of NO2 and you're going to form 1 mole of O2. So if we're going to write a ratio, we would have 4 NO2s to 1 O2. And so that what that means is that when we take a look at these concentrations, we're going to have a ratio of 4 to 1. So at any particular point in time, we're going to have a ratio of 4 moles of NO2 to 1 mole of O2. So that's pretty cool. That's pretty cool. All right, so so now that we saw what the NO2 and the O2 and the N2O5 are doing, let's take a look at the graph. Let's see what we can suss out from there. All right, so we got 3 curves on this graph. We've got this green one, which is representing NO2. We've got this purple one, which is representing N2O5, and then we got this blue one, which is representing O2. All right, now since the curve for NO2 is sweeping to the right, so it's going up, we know that this slope is going to be positive. N2O5, since it's starting from a concentration of 0, and it's going to a concentration that's just below, starting from a concentration of 0.02, and ending at a concentration that's under 0.01, this concentration is actually, that slope of that line should be negative. Okay, and if we look at O2, we start from 0 and we end up a little bit higher than N2O5, so that slope should also be positive as well. All right, Now, what's really cool, and we're starting to see part of this on the table, that from a certain point in time, from 300 seconds to 400 seconds, we can actually measure those changes. So we got the delta T, so that's a change in 100 seconds. If we measure the point from here all the way to the top, we could get the change in concentration. So if we take the change in concentration divided by the change in time, we can actually get the slope of that line between 300 to 400 seconds. That's going to be the rate of the chemical reaction in that time span from 300 to 400 seconds. Okay. Now, do we, and we did the same, we're doing the same thing for N2O5. We're also doing the same thing for O2. Now, here's the question. Can we do this for any other time? Yes, absolutely. So if I go over here to 100 and 200 seconds, I can make my same triangle that we did previously. Okay, so here's my triangles, and I can find the slopes of those lines, and those slopes would indicate the rate for that period of time from 100 to 200 seconds. So again, the way that we measure rate, that's going to be equal to the change in concentration over the change in time. All right. And we know that N2O5 is going down because we're losing reactants. NO2 and O2 are increasing. They're positive because we're making product. All right. Cool. And NO2 is going up higher than O2 because it's a ratio of 4 moles of NO2 to 1 mole of O2. Cool. All right, so let's do some math now. The rate of the reaction can be described in terms of the concentration change for any of the reactants, such as oxygen. So we can actually write a reaction rate for oxygen. We can say that the rate would be equal to the change in the concentration of O2 divided by the change in time. Now, we can also do the same thing for NO2, where the rate would be the change in the concentration of NO2 divided by the change in time. We could also do the same thing for N2O5, but this one, for N2O5, the rate would be the change in concentration for N2O5 divided by the change in time. Now, as we saw, the concentration, this rate would be a positive value for O2. It's going to be a positive value for NO2, and it's actually going to be a negative value for N2O5. All right, so what we're going to do now, let's analyze the change in concentration for all three of these substances from 200 to 300 seconds. So what we're going to do is take a look at this graph, and we want to analyze the concentrations. I'm boxing them up for all three of these in that time from 200 to 300 seconds. All right. So let's try this out. Let's focus on O2 for a minute. Now, if I go back to that table for O2, if I go back to the table for O2, this concentration table, the concentration of O2 at 300 seconds is 0.0040 molar. Concentration for O2 at 200 seconds is 0.0029 molar. All right, so those are my concentrations. So if I go over here, what I'm going to do is figure out, we're going to set this up as an equation. We're going to look at the change of O2 at 300 seconds. We're going to subtract it from the change in concentration, from the concentration of O2 at 200 seconds, and then we're going to divide that by 300 seconds minus 200 seconds. Okay. All right, so let's pop those numbers in. For 300, the concentration at 300 seconds, that was 0.0040 molar, minus the concentration at 200 seconds, from that chart, that was 0.0029 molar. If we divide this, it's going to be 300 seconds minus 200 seconds. Okay. So if I get 0.0040 minus 0.0029 divided by 300 minus 200, which is 100. If I do that, the rate should be between 2 to 300 seconds, 1.1 times 10 to the minus fifth molar per second. So that's my unit, molar per second. All right. Now let's check out the rate for NO2. So if I go back to the chart for NO2, concentration at 300 seconds is 0.0160 molar. Concentration at 200 seconds is 0.0115 molar. All right, so let's pop those into that value. So for NO2, we're going to do the same thing. The concentration of NO2 at 300 seconds minus the concentration of NO2 at 200 seconds divided by 300 seconds minus 200 seconds. Okay, and so our values were, at 300 seconds, we had 0.0160 molar. 200 seconds, we had the concentration 0.0115 molar. And then 300 minus 200 seconds, that's going to be 100 seconds. So if you take 0.0160 molar minus 0.0115 molar divided by 100, that rate should be 5.5 times 10 to the minus fifth molar per second. Now, there is another way to write this unit, because sometimes it's somewhat difficult to write fractions like this. So sometimes we'll represent the unit as this: molars times second to the minus first. And so that's the same thing as saying this fraction, molar per second. All right, let's check out the third one. So we got N2O5. So we have to go back to the concentration. We're going to look up the concentration for N2O5 at 300 seconds. We're going to look up the concentration of N2O5 at 200 seconds. And then we're going to divide that by 300 seconds minus 200 seconds. Okay, so going back to that table, concentration at 200 was 0.0142 molar. Concentration at 300 seconds, 0.0120 molar. All right, so that's what I'm going to put in here. So at 300, we had 0.012 molar, minus concentration at 200 seconds was 0.0142 molar, divided by 100 seconds. That rate would be a negative 2.2 times 10 to the minus fifth molar per second. All right, so now that I made a big deal about the negative sign, that we know that this is going to be a negative value because it's a reactant, the concentration should be going down. Now, because we know that, because we can look at the chemical reaction and know that since that's a reactant, the concentration needs to be going down, we report the slope. We report these numbers as positive, even if they come out negative. So even though this slope right here is negative, we know it's negative, we're going to report this rate as a positive because we can get that information from the reaction. We know because it's a reactant, the rate's got to be going down. Okay, so now here's where it gets kind of cool. What are the ratios between NO2 to O2 and N2O5 to O2? Well, we can get that from the chemical reaction. Remember, you had 2 moles of N2O5, and that gave you 4 moles of NO2 plus 1 mole of O2. So based on that, the ratio between NO2 to O2 should be a ratio of 4 to 1, and the ratio of N2O5 to O2 should be a ratio of 2 to 1. Okay? Now, if we go back to the table that we saw previously, if we go back to that graph, it actually did the calculations for us as to what the slopes were. So if we, let me write those slopes down. So for the concentration, for the rate for O2, that rate was 9.00 times 10 to the minus fourth molar per second. For NO2, that rate was 3.7 times 10 to the minus third molar per second. And then N2O5, that rate was 1.9 times 10 to the minus third molar per second. Now, are these the same rates? Are these rates the same as for the interval that we calculated? So, taking a look at these values from 300 to 400, are these the same values that we got here? No, they are definitely not the same. They are definitely not the same values. But are the ratios the same? And the answer is yes. The ratios are the same. So even though the rates are different, the ratios are still the same. All right, so what can we conclude from these two facts? Well, here they are. The first conclusion that we can make is this. The rates change over time since the concentrations change. Because the concentrations change. Okay. And then number two, the ratios are always constant. All right, so those are the two things that we can definitely get from what we're seeing. All right, so in this figure, what we're doing is focusing on just one curve. Just one curve. In this case, we're looking at NO2. So we know that the time is in. We know that the concentration's always increasing, and so what we're doing is saying, all right, if I want to know the slope of that line of that, what is the instantaneous rate of that point on the curve that I just marked out, what I'm going to have to do is draw a tangent line, and from that tangent line, I'm going to have to get the slope. And if I know that slope, then I know the instantaneous rate at a certain point in time. Now, what if I wanted to get the average rate of formation of NO2? What I would do is choose the time interval where I want to get that rate. So in this case, in this particular image, what we're doing is getting an average rate from 100 all the way to 600. Okay, so we use two specific points, and from that we get the slope out of those two points. Now, because you're going to have a wider time range, the average slope is it's not going to be very close to whatever that instantaneous slope is, or whatever that instantaneous rate is. Okay, so what do we call? Just to review a little bit of what we just talked about in this curve, what do we call the geometric figure drawn at 90 degrees to the concentration curve? That's called a tangent line. Okay, so we want to look for the line at t equals 0 and t equals 250. So again, here's the line for t equals 0, and at 250, here's that line again. Are they going to be the same? Do they have the same slopes? And they do not. Okay. Now the rate at t equals 0 actually has a special name, and it's called the initial rate. And this is a really important data point because it is only at this time that we can be sure that we have no reverse reaction. So we know that the reaction is progressing only in one direction. And that being said, so that gives us a pretty good indication, or a pretty good boundary, or start to looking at kinetics, at reaction rates. So in the next video, what we're going to start doing is take a look at how can we get some information about a chemical reaction. How can we look at experimental data and get some clear-cut stuff from a chemical reaction?